In this particular lecture, we will discuss about the representation of graph, and one of the most important aspects of graph is to how to represent these graphs. So, representation of graph will also be discussed in the form of adjacency matrices and adjacency lists. There are two ways that you can represent the graphs, that is adjacency matrix and adjacency list. I will discuss it in detail. So, the first is that what actually is a graph and how it is represented. So, a graph is nothing but it is a set of vertices, that is and edges, that is represented as G equal to V comma E. So, where V is the set of vertices and E is the set of edges. So, what do I mean by this is, suppose that you have a graph which have 3 vertices and every vertices is connected to each other. So, suppose the vertices is named as ABC. So, the vertices here will be ABC and the edges is the lines between them is referred to as the edges. So, if it is connected, every vertices is being connected to every other vertices. So, most probably there will be 3 edges. Okay. So, the edges can be represented from A to B, then B to C, then C to A. Okay. So, in this way. So, an edge between the vertices U and V is denoted as U comma V. So, similarly, so there are 2 types of graph. The first graph is referred to as an undirected graph and another undirected graph and a directed graph. So, in an undirected graph, you will see there are no arrows here, no directions, but in the directed graph or in the digraph, directed graph is also referred to as digraph. So, you will see that there will be a direction that is being given to every edge. So, this particular arrow will result in different interpretations in graphs. Okay. So, if it is an undirected graph, the edge between A to B is very close to B to A. But if it is a directed graph, the direction is from A to B. So, from A to B is not equivalent to B to A. So, that is how it differs. Okay. So, I'll directly give you an example here, so it will be easier. So, if you see here, the first example is the example of undirected graph. So, what happens in the undirected graph here, you can see that there are vertices from 0 to 5 and then there is an arrow between every vertices and then there are edges between 0 to 1, 0 to 2, 1 to 2, 2 to 3, 3 to 4 and 3 to 5 and 5 to 4 also. Now, if you take a look at it, how many vertices? The set will be 0, 1, 2, 3, 4, 5. The edges will be 0 to 1, 0 to 2 also, 1 to 2 also, 2 to 1 also. So, 1 to 2 and 2 to 1 is similar. So, that is also being represented. Then 2 to 3 and then 3 to 4, then 3 to 5 also, 4 to 5. Okay. So, 4 to 5, 5 to 4 is the same edge. Okay. Keep that in mind. But now look at the example of a digraph where there are arrows that is being placed. Okay. So, if you take a look at the vertices set will remain the same, that is 0, 1, 2, 3, 4, 5, but the edge set will slightly differ. Okay. So, now the edge is from 0 to 1. So, it is placed there, not 1 to 0, 0 to 1. Now, another edge will be 1 to 2, another edge will be 2 to 0, not 0 to 2, 2 to 0. Similarly, edge will be from 2 to 3, 3 to 5 and then 4 to 5 and 5 to 4. Okay. So, if you take a look at it, 4 to 5 and 5 to 4 are not same. Keep that in mind that they are not same because there is a direction that is being attached. However, the direction is bi-direction from 4 to 5 and 5 to 4, but this is not you will not consider it as same. Okay. So, these are 2 different set of edges. Keep that in mind. Okay. So, in digraph, when there are directions on the arrows, the interpretation of edges will change. But if there is no direction of the arrows, you can consider 3 to 4, 4 to 3 as same. But if there is a direction of the arrow, you cannot consider 3 to 4 and 4 to 3 as same. Also, if there is a double direction, means bi-direction also, then also you cannot consider both the edges as same, as given in the example 4 to 5 and 5 to 4. They are not same. Important point. Now, how to what actually is a path here is an edge may not have a weight. So what do I mean by weight is that if any value is written on edge, that value will be referred to as the weight of the edge. Suppose in the previous example we have seen that 3 to 4, in the edge 3 to 4 if I write 5 here, so the weight of 3 to 4 will become 5. Okay, so now if you take a look at this, the edge may not have a weight. So in this particular case, this is not compulsion that every edge will have a weight, and you cannot there is no compulsion that there should always be a weight, but a weight can also be there on the edge. A path in a graph is a sequence of vertices such that consecutive vertices have an edge between them, and V1 Vi plus 1 is adjacent to Vi. A path in a graph is simple if all vertices are distinct. It means that there is no repetition of the vertices in the sequence except possibly the last and the first one. Okay, so the length of a path is the number of edges that lies in the path. A cycle is a path, again cycle is also a path of length at least one such that the first and last vertices are equal. A cycle is a simple path with the same vertices as the first and the last vertices. So if you see, cycle is also there in the previous example, from 0 to 1, 1 to 2, 2 to 0. Okay, so if you are seeing here, first and last vertices is repeated in the cycle. So that is why the definition says a cycle is a simple path with same vertex as the first and last vertices in the sequence if the path is simple. For undirected graph, we require a cycle to have a distinct edges. Okay, so the length of the cycle is the number of edges in the cycle, and there are many problems in computer science such as route with minimum time and diagnostic, minimum shortcut path routing, traveling sales problem, etc., that can be designed using paths obtained by marking traversal along the edges of the graphs. Okay, so there is something called connected graphs or the connectivity in a graph. So what is connectivity? So a graph is connected if there is a path from every vertex to every other vertex. Okay, so we can see in the example ABC, every vertex can be reached from every other vertex. Okay, so if you want to reach C, it can be reached from AB. If you want to reach B, it can be reached from A and C. If you want to reach A, it can be reached from B, CBA. Okay, in the example A here, there is another graph that is unconnected or where there is no connection. So if ABC, if you can see in the example B, this is the simple graph that of ABC that is being given, then you can call it as connected graph. But if it is given with another graph and there is no relation between them, but you are saying that this is this one graph, then you can say that C and D is not connected with by any edge. So this is referred to as an unconnected graph. A connected graph is that graph where you can reach every vertex from any other vertex. The example of connected graph is G1 and unconnected graph is G2. Okay, so in the example G, there is a path between every pair of distinct vertices of the graph, therefore G is connected. However, G2 is not connected in a directed graph. Two vertices are strongly connected if there is a directed path from one to the other. Okay, so this is undirected graph both the time. But if this is a directed graph, so if you are able to reach every other vertex from the direction as well, then it is referred to as a connected graph. But if you are not able to do that, then this is not referred to as direct connected graph. Okay. So undirected graph means that two vertices are connected if there is a path between, includes them. Directed is two vertices are strongly connected if there is a directed path from any vertex to any other vertex. So there should be a path that is existent. Suppose the in a directed graph, it seems that the graph is being connected, but if there is no direction to reach a particular vertex, then this is not will be referred to as a directed graph. Keep that in mind. Okay. So moving on, how can you represent graphs? So graph can be represented in two ways. First way is adjacency matrix. Another way is adjacency list. So adjacency matrix is again adjacency matrix of graph V and G will be represented with n vertices, and it will be n by n matrix, that it will be represented by n by n. In this matrix, the entry of in the ith row and jth column is 1 if there is an edge between them, and from the ith vertex to the jth vertex in the graph G, if there is no such edge, then the entry will be marked as 0. It is very simple. Okay. So directly you can see the example here. The example here is that whenever there is an edge, you can write 1. Whenever there is not an edge, you can write 0. Okay. So how to build the adjacency matrix? You write the number of edges vertically as well as horizontally. So firstly, there are 5 edges. So write the name of the edge. So there are 5 vertices. So write the name of the vertices in the horizontal part as well as in the vertical part also. Now check. 1 to 1 there will not be an edge, so place it 0. 1 to 2 there is an edge, so place 1. 1 to 3 there is no edge, so place 0. 1 to 4 there is an edge, so place 1. 1 to 5 there is also no direct edge, you can place it 0 there. Similarly, from 2 to 1 there exists an edge, you can place it as 1. 2 to 2 there is no edge, so edge between edge with the similar vertices will be formed as 0, and edge will be different vertices will be formed as 1. Okay. So 2 to 3 there is an edge, so you can place it as 1. 2 to 4 there is no edge, so it is 0. 2 to 5 there is an edge, you can place it as 1. Okay. Similarly, for 3 also, 3 to 1 there is no edge, you can place it as 0. So 3 to 2 there is an edge, you can place it 1. So 3 to 4 there is an edge, you can place it 1. 3 to 5 there is also an edge, you can write it 1. Similarly, for 4 to 1 there is an edge, you can write 1. 4 to 2 there is no edge, you can write it 0. 4 to 3 there is an edge, you can write 1. 4 to 5 there is an edge, you can write 1. 4 to 4 there is no edge, so you can write 0. Similarly, for 5, so on and so forth, you can follow the same procedure. Similarly, there are some doubts that can arise from this arrangement, that suppose if we want to know that how much time will it take in finding the number of edges with n vertices. So because it is arranged in an adjacency matrix here, so in order to find the number of edges in a graph, if it is represented in the adjacency matrix, that it will be n square, because it is arranged in a n by n format. So it is a kind of a matrix, so you have to scan through it one by one. So because there is n square entries, you have to check every one of the entries to examine that how many edges there are. So you can directly say that n square is the complexity that is required for it. And suppose most of the entries in the matrix are 0. So this is another question that can arise when a graph is very sparse. So how much time is needed to find m number of edges in a graph? So if there are the graph is very sparse, so it means that there will be less number of edges in there. So you can say it will take less time, so the complexity can become O raised to power O, a big O of edges plus the number of vertices. So edges will, if it is smaller than the half suppose if the edges is lesser than n 2 by 2, then it is will be referred to as, it will take a lesser time. Okay. So another way that you can represent a graph is a adjacency list here. So the adjacency list of a graph or a digraph is a set of linked list, one linked list for each vertex. The node in the linked list contain all the vertices that are adjacent to vertex of the list, all the vertices connected to it by an edge. The figure that is being shown here represent the adjacency list of the graph. Now check, this is again based on a similar example here. So what is happening here, the vertex 1, that is 1, if you check here, it is connected with the 2 and 4. So just extend the adjacency list to 2 and 4. For vertex 2, you can see that it is being connected to 1 and 3. So you can extend it to 1 and 3. Similarly, for vertex 3, you can see it is connected to 3 different vertices, that is 2, 4 and 5. So you can extend the list to 2, 4 and 5. For vertex 4, it is again connected to 3 different vertices, that is 1, 3 and 5. So you can simply write it in a adjacency list in the form of a linked list. And in the end, for vertex 5, it is connected to 2 different vertices, that is 4 and 3. So you can write it in this way. So again, this is another arrangement that you can do. Instead, if you do not want to use a adjacency matrix, you can also represent the graph with the help of a adjacency list. Okay, there are few questions that can arise here. So what is the storage requirement for adjacency list of any graph? So for storing n value, means n vertices will be there. So for storing n head nodes, we require log complexity. Okay, so log of base 2n bits. So for storing the list node for each head n nodes, so we only require log n and log of e. Therefore the total storage requirement will be from log 2 of n in the bracket is log base n base 2 n plus log base 2 n e. Okay, so it's a lesser complexity as compared for storage as compared in the adjacency matrix, because you have to the complexity was n square. So what is the time complexity in determining the number of edges? So it is again lesser as compared to the adjacency matrix, because you have to scan every entry there, so it will become n square. But here it can be only done with the big of complexity of n plus e, where n is the number of vertices and e is the number of edges. Okay, so use of adjacency matrix or adjacency list is truly dependent upon what is your problem or what is the specific case. So in some cases adjacency matrix perform better, in some cases adjacency list perform better. So the type of algorithm can be used for solving a problem, and type of input graph, like if you have dense sparse graph or sparse graph, these are all the situations where you will see and you will take care of that, whether to represent a graph in a adjacency matrix or whether to represent a graph in adjacency list. So it is totally dependent upon the problem also. And if you can see in general, the adjacency list has a lower storage value, and as well as the time complexity that is required here is also less. Okay, so in this particular lecture we have seen the representation of graph, what is a graph, and in the next one we will see about the depth first search and the breadth first search. So thank you.